Hello everybody. I have to apologize for a little bit late starting, and one more apologize that I am still is not ready with exam program, I mean exam questions. I'm really sorry, but other duties, too many duties now are homeworks of students to check, and that's it. Okay, I hope I'll finish it until next week lectures. But in any case, the exam is scheduled on 21st of June, so a lot of time ahead. So, today's section, 26.1, representations by Taylor series. I'll start with an example. Which shows what kind of problems appear. So we consider the function e to the power x. Okay, let us form its Taylor series. What is it? And we are talking about Maclaurin series. So Maclaurin series. And if we compute a derivative, so in fact any derivative of exponent function is the exponent function itself, hence the value is 1 of any derivative at 0. Hence the Maclaurin series will be as follows. Like that. And the question is it true or not, this equality? We saw in the last example of former lecture that the existence of a Taylor series doesn't guarantee that our function is represented by the Taylor series. So what can we say about power series in the right hand side? What is about radius of convergence? Radius of convergence we can easily compute by a formula. So here we have coefficients, okay, n 1 over n factorial. So by the formula radius of convergence equals to such a limit, if it exists, we find that it is n plus 1 factorial over n factorial, that is limit of n plus 1 or infinity. So radius of convergence is infinity, hence our series converges for every x. So for arbitrary x in R, the series converges. That is because of the theory of general theory of power series. if a power series has a radius of convergence infinity, then it converges for arbitrary x. And in particular, by term test, or necessary condition, in other words, we deduce that the limit as n tends to infinity x to the power n over n factorial equals to 0. Once again, remember, for arbitrary x. And this fact will be used a little bit later. And this example shows what kind of problem appears. So we need to check if indeed the sum of our function equals to our exponent. That is the question. We know from former example that the sum of a series, of a Taylor series, need not to coincide with the function which was expanded. Okay, so the first result in this direction, theorem 1, sufficient condition for representation by Taylor series. If f is infinitely differentiable on an interval, let's say x naught minus delta x naught plus delta, and there exists m, a constant m, of course positive, right, such that for all x in our interval and n natural and also 0, inequality as derivative at x less or equal to m holds, then the equality f as derivative at x naught over n factorial x minus x naught or n is valid for every x in x naught minus delta x naught plus delta. Okay, of course delta should be a positive, otherwise makes no sense to consider it. So what this theorem says? It says that once we have a bound for any derivative at arbitrary point of our interval, we can represent our function by its Taylor series inside this interval where our derivative is bound. Okay, now let us prove it. So proof. Use Taylor formula with remainder in Lagrange form. Lagrange form. So what it says, that our function can be represented for arbitrary n. We can do it because by our supposition the function has derivatives of any order, and there is a remainder which has a form and derivative of the order n plus 1 at a point xi over n plus 1 factorial times x minus x naught power n plus 1. That is the remainder of Taylor formula in Lagrange form, where xi is between x naught and x. So once we have it, then we deduce immediately. What we deduce immediately? Look, for arbitrary x in our interval where all derivatives exists and are bounded by our supposition by constant, we can write the following estimate. So we have the following estimate: less or equal, I rewrite what remains in the right hand side, derivative of order n plus 1 at a point xi over n plus 1 factorial times x minus x naught power n plus 1. And now look, by our supposition arbitrary derivative is less or equal capital M, and then I'll write the following: ratio, and you see, look at the consequence of example 1. The consequence of example 1 shows immediately that the right hand side tends to 0. This tends to 0 as n tends to infinity. Hence, the left hand side has to 0 as well. And that is what we wanted to prove. So it means, because what is here, Taylor polynomial, is nothing else but the partial sum of the Taylor series of the function f of x. Hence, the theorem is proved. How it works? So, more examples. And in fact, those examples maybe I'll collect them as a subtitle in our section. So, main expansions of elementary functions in Taylor series. In fact, we are talking only about Maclaurin series. So the first one is for exponential function. So what was written with question sign, now we can write without question. So x in R. This is valid now for all x in R. Why? We apply theorem 1. So proof. F of x equals to e to the power x, and derivative equals to e to the power x once again. Hence, for arbitrary finite interval minus delta, okay, for arbitrary delta greater than 0, we have the following estimate for arbitrary x in the interval minus delta delta, and for arbitrary n, natural and also 0, we have the following estimate as derivative at x, which is e to the power x less or equal than e to the power delta. That is a finite number which we can take as a constant capital M from theorem 1. Hence, by theorem 1, this expansion is valid for arbitrary interval minus delta delta, and hence it is valid for arbitrary x as well. Okay. So now next expansion is for a trigonometric function. Let's start with cosine x. So cosine x equals to the sum and from 0 up to infinity minus 1 to the power n x to the power 2n over 2n factorial, and once again this is valid for all x real, for all x real. And proof. So here once again we apply theorem 1. Now the function f of x equals to cosine x. So as derivative is equal to cosine of x plus n pi over 2. This formula was checked during first semester. And then we can write an estimate for arbitrary x in R and for arbitrary natural n and also 0. We have the following estimate. Arbitrary derivative is less or equal than 1. So the constant the constant m from theorem 1 is equal to 1. Hence, the representation is proved for arbitrary x. So the estimate is valid not only for a certain delta, but for arbitrary delta. Third of main expansions is related to another trigonometric function, sine x, that is equal to sum n from 0 up to infinity, minus 1 to the power n, x to the power 2n plus 1, 2n plus 1 factorial, x in R, coefficients. I don't want to check coefficients because we did it when considered Taylor formulas with remainders in Peano form, and of course coefficients are the same, hence we don't need to spend time to deduce them once again. Now, once again, similarly, we apply theorem 1 with function sin x and derivative is equal to sine of x plus n pi over 2, and same estimate as for cosine is valid for sin x as well. Sin x as well. Okay, now now for cosine hyperbolic and sine hyperbolic we may use expansion 1, so corollaries of 1 are first cosine hyperbolic x equals to the sum x to the power 2n over 2n factorial for all x in R, and sine hyperbolic x is analogous expression but with odd powers of x. By the way, you see similarity between trigonometric and hyperbolic functions, just alternating sign for trigonometric functions disappear for hyperbolic functions, that's all. And why these are indeed corollaries, I'll check it for cosine hyperbolic only, proof. So cosine hyperbolic x is e to the power x plus e to the power minus x over 2. So we substitute our formula for exponential function. So what we have, 1 over 2 times n factorial minus x to the power n plus x minus x minus 1 to the power n times x to the power n. And you see, once n is odd, this term in brackets equals to 0, and if n is even, then we have 2 times x to the power n, cancel 2, and we obtain what is written here. So n equals to 2m, we can write m from 0 up to infinity, x to the power 2m over 2m factorial. Analogously, we proceed with sine hyperbolic as well. Okay, now for next expansions, for next expansions, I need an additional fact which I didn't prove before, so let me do it now, like a lemma, or maybe theorem. Yeah, maybe theorem. It's quite important. So let me formulate it. Okay, firstly, how it is called. Taylor's formula. Taylor's formula with integral form of remainder. Well, remainder in integral form doesn't matter. So I've formulated not in a full generality to make everything easier to prove. So if f is continuous on, let's say, x naught minus delta, x naught plus delta together with its derivatives up to order up to n plus 1th order, then we can write the following estimate. F of x for all x in x naught minus delta x naught plus delta, we can write the following representation. Okay, from 0 up to n. Case and x naught over k factorial x minus x naught power k plus 1 over n factorial integral from x naught up to x, derivative of order n plus 1 of t times x minus t to the power n dt. And of course we use here the agreement, same agreement as usually. I mean that if x is less than x naught, then we should change limits with minus sign before the integral. Proof. Let's start with n equals to 1. So we start with Newton-Leibniz formula. Newton-Leibniz formula or fundamental theorem of calculus. So what we can write? We can write, so our function f is primitive for f prime by the definition. So we can write Newton-Leibniz formula like that. Then we'll apply integration by parts. Integration by parts. So I consider x as a fixed parameter. So differentials are taken with respect to variable t. X is fixed. So x is fixed, remember. Then to apply integration by parts formula, I represent it as dx minus t, and if we differentiate with respect to t, then minus appears, so I should put here minus. Then applying integration by parts, I write f prime of t times x minus t, then substitute t equals x naught, t equals to x, and then minus, and we have another minus here, so plus integral from x naught to x. Now we differentiate f prime, and we obtain f double prime of t, x minus t dt. What remains? So if we substitute t equals to x, we obtain 0. So this term is equal to f prime at x naught times x minus x naught. And minus disappears because of lower substitution, lower limit substitution. And it means that indeed we obtain the formula for n equals to 1. So k starts from 0 to 1, f of x equals to f of x naught plus f prime at x naught times x minus x naught. Okay, let me write it down explicitly. So I collect everything what was proven. Double prime of t times x minus t dt. And you see that is indeed the Taylor formula with remainder like it is written here. Substitute n equals to 1, second derivative, so everything is precisely like here. Okay, so we continue by induction. N equals to 1 we have made. So okay, let us suppose we have proved. So it means I have the following formula. And we need to check, so this formula is true, and we have to check for n equals to m plus 1. So f of x equals 2, we need to prove it, m plus 1, k derivative at x naught, k factorial, x minus x naught power k plus 1 over m plus 1 factorial times integral f derivative of order m plus 2 times x minus t power m plus 1 dt. So that is we need to prove. And it is clear how to proceed here. So we look at the right hand side of the induction hypothesis. So let me rewrite this integral, which we have derivative of order m plus 1 of t times x minus t power m dt equals 2. So remember, x is fixed. Okay, let's continue. So we proceed like we did for n equals to 1. We apply integration by parts formula. Okay, let me do it using standard table. U equals to what, dv equals to what, v equals to du equals to. So we take u derivative of order m plus 1 of our function, dv is everything else, right? And if v is like that, then when we integrate over t, we obtain minus 1 over m plus 1 times x minus t to the power m plus 1. So it is easy to check that if you differentiate it with respect to t, remember x is fixed, is a constant now, then we obtain precisely this function x minus t to the power m. And du is, if we take differential, we obtain derivative of order m plus 2 times, okay, let it be of t, dt, okay? So that is the table to apply for integration by parts. And if we substitute, so u times v, remember we have 1 over m factorial, it gives m factorial times m plus 1 factorial times m plus 1, sorry, times derivative of order m plus 1 of t times x minus t power m plus 1, substitution t from x naught up to x, then minus, because of this minus it becomes plus 1 over, okay, what is the constant? The constant is precisely m plus 1 factorial. And integral from x naught to x, v times du, so derivative of order m plus 2 of t times x minus t power m plus 1 dt. So the only thing what remains is to observe that this expression, okay, maybe that one, the substitution gives immediately 1 over m plus 1 factorial times, so we substitute t equals to x, we obtain 0. Then we substitute t equals to x naught, put minus sign, cancel that one, and it gives derivative of order m plus 1 at x naught times x minus x naught power m plus 1. And that is precisely extra term which is added to the sum of the first m terms which we had before. So it means the proof is completed and the theorem is proved. Okay, now I want to apply this formula for the next expansion. So I will erase everything else. The result of that formula. Now we want to generalize Newton binomial formula. So recall what is Newton binomial formula. It looks like 1 plus t to the power n equals to, maybe to the power, okay, sum k from 0 up to n, n k, t to the power k. That is a particular case of binomial formula, right? Where nk, binomial coefficients, is given by k factorial times n minus k factorial. And now I'll write it in the form which is more suitable for our purposes. That is n minus k plus 1, so on up to n. Maybe in inverse order. N times n minus 1, so on n minus k plus 1. What remains is like that. And what is important, that here we can take, instead of an arbitrary, the last ratio, we can take arbitrary real number alpha, and it gives generalized binomial coefficient, which is defined by the following formula. That is generalized binomial coefficient alpha k. And now we are ready to formulate next main formula, that is fourth formula in Maclaurin representation of elementary functions. 1 plus t to the power alpha is equal to sum k from 0 up to infinity, alpha k, t to the power k, or if you want, I can write explicitly alpha times alpha minus 1, so on, alpha minus k plus 1 over k factorial times t to the power k. The radius of convergence here is equal to 1, so it converges only for t less than 1. Okay, why I wrote t instead of x? Let me change to x. I will use t of the integration. Okay. And you see that if alpha is natural, then this is precisely Newton binomial formula. Why? Because if alpha is natural, then when we start to multiply here, sooner or later, more precisely when k will be equal to n plus 1, 0 multiplier appears, hence all other multipliers, coefficients are zeros, and only first n plus 1 terms are do not vanish. First n plus 1 term do not vanish if alpha equals to n natural, right? So it means that we need to prove for alpha not natural. And of course, 0 is also should be excluded because it makes no sense. And yeah, for k equals to 0, maybe I should write separately. This is an agreement, right? Alpha 0. Generalized binomial coefficient alpha 0 is equal to 1. Okay, so now proof for this formula when alpha is not natural or 0. So here we'll use Taylor's formula with integral form of remainder. So f of x is 1 plus x power alpha. And we can write, so nth derivative, or maybe kth derivative at x, what is it? 1 plus x power alpha, we differentiate k times. And you see every time when we differentiate, we apply chain rule, but derivative of 1 plus x equals to 1, so no extra multipliers appear. And when we differentiate power alpha, we obtain alpha times alpha minus 1, so on, times so many terms, how many times we differentiate. That is like that. 1 plus x to the power alpha minus k. That is the result of differentiation, and that is why I should suppose here alpha is not natural to... Yeah, in fact, this formula is valid for alpha natural as well, because one of multipliers will be 0. But, okay, there is a trivial case, we will not consider it. So, derivatives are determined, and then let me rewrite the formula with remainder in the integral form. So x naught is 0, so we are talking about Maclaurin formula once again. So if we substitute 0 here, that is 1, so we have alpha times alpha minus 1, so on, alpha minus k plus 1 over k factorial times x to the power k, and plus remainder. Okay, I will write remainder like that, where Rn of x equals to 1 over n factorial, integral from x naught up to x, then I substitute derivative for the n plus 1, that is alpha minus k equals to n plus 1, so alpha minus n over, oh no, not over, then 1 plus t power alpha minus n minus n minus 1, right? Minus 1 times x minus t to the power n dt. That is the remainder. Okay, so I want to estimate this Rn. So we need to prove that Rn tends to 0 as n tends to infinity for x less than 1. So we should consider x less than 1 in modulus. And I can rewrite them n plus 1 and minus, I can rewrite Rn as follows. So alpha times alpha minus 1 so on times alpha minus n over n factorial. You see, this is not precisely alpha n, it's slightly different. And then integral from x naught up to x 1 plus t to the power alpha minus 1 times x minus t over 1 plus t to the power n. So I collect all terms in power n. Now, let us denote phi of x minus t over 1 plus t. So by definition, phi of t, x is fixed. Phi of t is x minus t over 1 plus t. Let us investigate, let us try to estimate this function when t is between 0 and x. So, let me compute phi prime of t. Remember, x is fixed. So, derivative of numerator minus 1 times 1 plus t minus numerator times derivative of the denominator is 1 plus t squared, and that is minus t plus t minus 1 plus x over 1 plus t squared. And you see that is less than 0, for all x from minus 1 to 1. We consider modulo x less than 1. So the function phi is strictly decreasing, and then we have two possible cases. So first case, if x t is between 0 and x is non-negative, then so we know phi is decreasing. So what can we say about phi of t? The largest value of phi will be at 0 and it is equal to x, and minimal value at x and it is equal to 0, right? Because of monotonicity of phi. And analogously, if x is non-positive, then once again phi is decreasing. So what are maximal value? Maximal value will be, at which point? From x to 0. So at x it will be largest. At 0 it will be minimal. Remember, x is negative here, right? So in any case we have modulo phi of t less or equal modulo x. For arbitrary case, when t is between 0 and x, doesn't matter which sign of x we have. Okay, then what we obtain after that? Remember, I want to estimate Rn of x. Rn of x that is less or equal. Okay, let me write coefficient firstly. And factorial. Then integral. Okay, I'll write integral from x0 to x. Okay. X to the power n I can put after, so what remains 1 plus t to the power alpha minus 1 dt. Okay, times modulo x to the power n. So that is phi of t here, power n we estimated by x to the power n. Okay, this can be estimated by a constant, because look, if x is positive, then we can replace x by 1. If x is negative, oh sorry, not x0, from 0, it is everywhere. From 0. Okay. I consider Maclaurin series, integrate from 0. So if x is negative, then once again I replace by minus 1, so that is less or equal to a constant c. So c is, let's say, maximum of integrals from 0 to 1, 1 plus t alpha minus 1 dt, and integral from minus 1 to 0, 1 plus t power alpha minus 1 dt. Both are, oh, from minus 1 it is not good. No, I'm sorry. Let it be c of x alpha, that is equal to, sorry, I have a problem when x approaches to minus 1. That is different story, but I don't need to avoid x, in fact. Just a constant. For arbitrary fixed x, that is a constant, right? Okay. Then what remains? Look at the power series. So consider power series. Sum, and from 0 up to infinity, let me write the coefficient which we had. Oh, by the way, I should put here modulus as well, because alpha may be negative. Alpha minus 1, so on alpha minus n over n factorial times x to the power n. That is a power series. Radius of convergence for this power series we can compute by limit of an over an plus 1. Coefficients, these are, that is a coefficient an, let's say, and it gives, if we divide, then we obtain, okay, what we obtain here. When I add one term extra to an plus 1, it remains. So n plus 1 factorial was in denominator here, will be numerator, and alpha minus n minus 1 is here. So modulus, and it gives 1. So radius of convergence is 1. Hence, by properties of power series, this series, this series is absolutely convergent for x less than 1. So every power series is absolutely convergent inside its interval of convergence. But then by term test, we obtain that the limit as n tends to infinity of modulus of a term, that is alpha minus 1, so on, alpha minus n over n factorial times x to the power n, is equal to 0. Limit equals to 0 by term test. And what it means, look at the estimate of Rn of x. So for arbitrary x in modulus strictly less than 1, we have that our remainder is estimated by a constant for a fixed x times something what tends to 0. And it means that Rn of x, so as a conclusion, Rn of x tends to 0 as n tends to infinity for arbitrary x modulo x less than 1. And that's all. So we have proved that the remainder tends to 0. So the formula, that is, sometimes it is called binomial series. Binomial formula is here, and binomial series is for arbitrary alpha. That is binomial series. Okay, and the last of main expansions is a particular case. In fact, one. Binomial series we know, because it is nothing else but the sum of geometric progression. So one particular case. Let us consider one particular case. So particular case, alpha equals to minus 1. What do we have then? Alpha equals to minus 1. 1 plus x minus 1 equals to sum k from 0 up to infinity, minus 1 times minus 2, so on, up to minus, okay, what we have here, minus 1 minus k plus 1, that is minus k, over k factorial times x to the power k, and that is, you see, k factorial times minus 1 to the power k, x to the power k. And of course, we recognize immediately the formula for the geometric progression, right? With denominator minus x. Infinite geometric progression. And by the way, when it is valid, that is also an interesting case. So look, if you substitute, no, it is valid only for modulo x less than 1, strictly less. No exclusions here, of course. Okay. And So we knew this particular case, but now what is a consequence of this particular case? That is fifth of main expansions. There are 5 main expansions: exponent, sine, cosine, binomial, and logarithmic. So let me, okay, I forget which I used, ln or log, which notation I used for natural logarithms. Logarithm of 1 plus x is equal to sum n starts from 1 up to infinity minus 1 to the power n plus 1 over n x to the power n, and this is valid in fact for minus 1 less x less or equal to 1. Okay, proof. We integrate the series 1 plus x minus 1 equals to sum. Okay, I will write like that, e to the power k on over interval 0x, let's say, right? We can do it when x is strictly less than 1. That is possible. We know that every power series can be integrated over interval which lies inside the circle of convergence. The interval of convergence, sorry, to integrate only for real case. So if we integrate 1 plus t minus 1, we obtain precisely logarithm 1 plus x, and if we integrate from 0 to x every term here, we obtain precisely sum, okay, I will write firstly like that, minus 1 to the power k x to the power k plus 1 over k plus 1, and if we replace k plus 1 by n, we will obtain immediately k plus 1 equals to n. We obtain immediately our expansion for logarithm. Okay, here n minus 1, but it is the same as n plus 1 minus 1 to the power. So we proved it for modulo x less than 1, right? Now, to complete the proof for x equals to 1, what remains? Let us use second Abel's theorem. So we have an expansion, right? And if we substitute x equals to 1, then the series converges by Leibniz test. By Leibniz test. Hence, by second Abel's theorem, what we deduce? So what says second Abel's theorem? If a power series converges at a point, then the sum of this series is continuous on so the sum of our series is continuous on 0, 1. That is a corollary of second Abel's theorem. But we know that this is logarithm 1 plus x for x strictly less than 1. So you see, we have two functions which are equal for modulo x less than 1. We know logarithm is continuous on 0, 1, and the sum is also continuous. Hence, they are equal at 1. So, we obtain logarithm 1 plus 1 equals to the sum of our series minus 1 to the power n plus 1 over n. That is logarithm 2, right? That is nice consequence of second Abel's theorem, second Abel's theorem. So we have such a sum 1 minus 1/2 plus 1/3 minus 1/4 plus so on equals to logarithm 2. By the way, as we know, this series converges conditionally. So by Riemann's theorem, we can rearrange terms of our series in arbitrary order to obtain an arbitrary value of the series as a result. So, okay. Okay. Maybe one more example. So now I have 3 minutes. What to do? Binomial series. Okay, maybe a corollary, couple of corollaries of binomial series. They need more corollaries. Maybe to finish with, I'll introduce, let's compute minus 1/2 or 1/2 minus 1/2 minus 1/2 over n, those binomial coefficients, because we'll meet them later, so I want to compute them now. So what is it? We have n terms with minus, so minus 1 to the power n over n factorial times 2 to the power n, and in numerator we have 1 times 3 times so on up to n minus 1. Minus 1 minus 2n plus 2 minus 2n plus 1, yeah, 2n minus 1, yeah. And that is denoted by double factorial, so 2n minus 1 double factorial. Also, 2n double factorial we have in denominator. That is a particular case when binomial coefficient can be expressed in terms of so-called double factorial. So what is double factorial? So double factorial of odd number is a product of all natural odd numbers from 1 up to n minus 1. Analogously, double factorial of even natural number is product of all even natural numbers. Because look, what is n factorial times 2 to the power n? Let me write it down here. N factorial times 2 to the power n. 1 times 2, so on up to 2n, times the same amount of multipliers equal to 2, each of them. And then if we arrange in a different way, so 2 times 1, 2, 2 times 2, 4, so on. Sorry, here 2n, the last n factorial. Then the last is 2n. So the product of all even natural numbers from 2 up to 2n. That is 2n double factorial. Okay, let me stop here. Thanks for your attention.